Let us start today's lecture. In our today's lecture, we'll start with rotor construction of a three-phase induction motor. Principally, there are two types of rotor for three-phase induction motor. One is squirrel cage rotor, squirrel cage rotor. Sometimes it is called cage rotor. Another type is wound rotor. I will describe both types of rotor, but squirrel cage rotor is widely used induction motor rotor. Almost 90% of induction motors are squirrel cage type, and it has some advantages, especially the construction principle is simple and this type of rotor is very robust. So let us start the description of squirrel cage type rotor. So squirrel cage rotor, as the name suggests, the construction looks like a squirrel cage type. So we'll have a shaft here. In both sides there is a shaft on which this squirrel cage rotor is situated. These are end rings and they are shorted. They are connected by some iron bars. So if we consider this is an iron bar and another iron bar will be here, another iron bar will be here, this is another iron bar, and at the back there are other iron bars. These iron bars are generally made of aluminum or copper, so they act as conductor, and these two rings are named as end rings. So they are named as end ring, and we have bars generally made of aluminum or copper, and this is shaft, and these two shafts are connected with two bearings. We'll have one bearing here, another bearing here, so that this rotor can move freely on the top of this bearing. So these are bearings. This cage looks like a squirrel cage, which was used in different circus to run rat inside this cage. It was a game show. Nowadays these things are obsolete. From that the name came squirrel cage rotor. So we have conducting birds. At the both side there are end rings and they are shorted in the both side. That's all, and this is the complete construction of a squirrel cage rotor. Now whenever we have this type of stator, for example this is a stator configuration, and this stator is fed from a three-phase supply, phase A, phase B and phase C. So this is the side view of the stator, and if we place this type of rotor inside this hollow part, the rotor will start rotating. So if we place the rotor inside this hollow part, so this rotor, this is the side view, we have bars connected from one side to another side, and we are giving a three-phase supply. Though this stator and this rotor, they are not connected, but whenever we'll give three-phase supply, this rotor will start rotating. Why it happens, we'll explain this after some time. The fact is, whenever we'll give a three-phase supply, there will be a creation of rotating magnetic field, that is virtual rotating magnetic field, north pole here, south pole here, and it will start rotating in one direction. And the speed of this rotation is called synchronous speed, and it is defined by ns equal to 120 fe over p, where fe is the frequency of the supply current, and the direction can be changed by changing the connection of any two phases. So what we said, whenever we gave a three-phase supply here, there will be creation of rotating magnetic field, and we are placing a rotor with this configuration inside this hollow part. Just after giving the electrical supply, this rotor will start rotating. Now the question is, why does this rotor rotate? So if we write it, why does the rotor of an induction motor rotate? This is the question. Sometimes this question is asked in another way: how does an induction motor start, or what is the principle of operation? So all the answers will be given now. Now let us draw the zoomed version of this portion that will look like this. Suppose we have stator and this is the rotor. The rotor parts are here. This is the portion of this stator and rotor configuration, and this is the air gap. We have very small air gap here, and as we have virtual north pole here, so fields are coming out from north. Fields are coming out from north pole. So field direction is downward. Now, whenever we give three-phase supply, this magnetic field starts rotating. We are taking, for the time being, it's rotating in the anti-clockwise direction. And the speed of this rotating magnetic field is termed as ns, which is equal to 120 fe over p, where f is the frequency of the supply current, as I told earlier. P is the number of poles per phase. At this juncture, I want all of you to keep this in your mind, that this ns is the speed of the rotating magnetic field, and as this ns is synchronous with the supply frequency, that's why it is called synchronized speed. And this is not the rotor speed. Rotor speed is different. This is the speed of rotating magnetic field. At the very initial moment when we give this three-phase supply, at that moment rotor is stationary. However, once we give the three-phase supply, there is a creation of rotating magnetic field. At that instant, it starts rotating with the synchronous speed. But rotor is at stationary at the very beginning. So this field, while rotating, cuts the rotor bars. This is something like this. We have parts and magnet, north pole, and it's rotating in this direction or moving in this direction. This field are cutting this wire. So what will happen? There will be an EMF induced in this rotor bar. As we have EMF induced in this wire, as we learned it from our very first few lectures. So there will be an induced EMF in these rotor conductors, and since the rotor conductors are short circuited at the both side, so as I told you earlier, these bars are short circuited at the both side, so current will start flowing through these rotor bars. Now what will be the direction of the current that is flowing through these rotor bars? In order to get that, we need to apply Fleming's right hand rule. Because this is generator action, we are giving a motion in the magnetic field and getting the current as an output. So this is generator action. So what is the direction of the force? Now the magnetic field is rotating in the anti-clockwise direction. So with respect to this bar, the field is rotating in the anti-clockwise direction. If we consider with respect to this magnet field or magnet, that this bar is rotating in the clockwise direction. So we can say the direction of the force that is defined by the direction of the conducting wire. So the direction of the conducting wire, if we consider this magnet is at static position, we can figure out with respect to this magnet the bar is moving in the opposite direction. So the direction of the force will be in the rightward direction, and the direction of the magnetic field is downward. So this is B direction. So what will be the direction of current? If we apply Fleming's right hand rule, we'll find that the direction of the current into the page. So we can say the direction of the current will be into the page. So whenever there is a relative speed between this magnet and this bar, this magnetic field will cut this bar and there will be a creation of EMF, and that EMF will cause the current to flow because the circuit is filled and in the both sides they are short circuited. So it will cause the current to flow through this metallic bar. And what will be the direction of this current? We can figure it out by you applying Fleming's right hand rule. Now we have a current carrying conductor which is placed under a magnetic field. So whenever we have current carrying conductor that is placed under a magnetic field, that will produce a mechanical force. So what will be the direction of that force? Now we'll consider that we have current carrying conductor, and due to that current these bars will experience a force because it is placed under a magnetic field. Now what will be the direction of that force? Let us figure it out. We have current carrying conductor and magnetic field is downward. Now if we apply Fleming's left hand rule, because we are giving current under a magnetic field and we are getting force as an output, so this will be the motor action. So if we apply Fleming's left hand rule, we'll get the direction of force. Now applying Fleming's left hand rule, we are getting the direction of force is in the left side. So direction of force which is exerted on the rotor bars, that is directed toward left side. This we are applying Fleming's right hand rule here, and this current is caused by the rotating magnetic field, and after producing this current, that current will experience another force because it is placed under the magnetic field. So the direction of that force due to that current can be found out by applying Fleming's left hand rule. So due to this force, this rotor bar will experience a force in this direction. So what will happen whenever this rotating magnetic field will start rotating? There will be current flowing through these rotor bars, and due to that current, the rotor bar will experience a force in this direction, in the direction of the rotation. So this rotor will start rotating in the same direction of the rotating magnetic field. So we can say the rotor will start rotating. This is how the induction motor starts, and this is why the rotor of an induction motor rotate. Even though this is stator and rotor, they are not connected. Connected means like DC motor, we did not give any supply to the rotor side. So we are giving supply in the stator side only, and we are placing a rotor having this configuration, and once we give this three-phase supply, the rotor starts rotating because of this force. The sum of the mechanical forces on the rotor conductors produces a torque which tends to move the rotor in the same direction as the rotating magnetic field. The cause of the rotation of the rotor can be explained by Lenji's law as well. According to this law, the direction of rotor currents will be such that they tend to oppose the cause of producing them. Now, the cause producing the rotor currents is the relative speed between the rotating magnetic field and the stationary rotor conductors. Hence, to reduce this relative speed, the rotor starts running in the same direction as the stator field and tries to catch it. Because whenever there is a relative speed between this rotating magnetic field and the rotor bars, so there will be a cutting of magnetic field, and due to that cutting of magnetic field there will be induced EMF in the rotor bar, and due to that induced EMF, as the rotor bars are short circuited in the both sides, there will be a current flowing through the rotor bars. So what is the cause of creation of this current? The relative speed between this rotating magnetic field and the rotor bars. So the rotor will try to reduce that relative speed between this rotating magnetic field and the rotor bars, so that the cause of creation of this current can be demolished. In order to do that, the rotor will start rotating in the same direction of the rotating magnetic field, and it will try to catch the stator field. So this is the basic principle of operation of a three-phase induction motor with squirrel cage type rotor. Let me summarize the operation in brief. Whenever we'll give a three-phase supply, there will be a creation of rotating magnetic field, and the speed of that rotating magnetic field will be Ns equal to 120 Fe over P. When this rotating magnetic field starts rotating, there is a relative speed between this rotating magnetic field and the rotor. So this field cuts the rotor bar. Due to that cutting of that magnetic field by the rotor bars, an EMF will be induced in the rotor side. And due to that EMF, as the rotor side is short circuited, there will be a current flowing through the rotor bars. According to the Lenji's law, that will oppose the cause of creation of this current. So what is the cause of creation of this current? The relative speed between this rotating magnetic field and the rotor. So in order to reduce that relative speed, the rotor will start rotating in the same direction of the rotating magnetic field. Now, if we want to change the direction of the rotor, what we need to do? We need to change the direction of rotating magnetic field. How can we change the direction of the rotating magnetic field? By changing the supply of any two phases. So if we change the supply of any two phases, the direction of rotating magnetic field will be reversed, and the direction of the rotor will also be reversed, because in order to reduce the relative speed between the rotating magnetic field and the rotor will start rotating in the same direction of the rotating magnetic field. This is the operating principle of a three-phase induction motor with a squirrel cage rotor in brief. Next, we'll discuss about the speed of the rotor of an induction motor. Let us consider the speed of a rotor of an induction motor is denoted by Nr. So, the speed of the rotor can be denoted by Nr. Ns is the speed of the rotating magnetic field and Nr is the speed of the rotor. As we discussed earlier, that whenever we'll give three-phase supply, there will be a creation of rotating magnetic field, and that rotating magnetic field will cut the rotor bars, and an EMF will be induced and current will be flowing through the rotor bars. In order to oppose that current, the rotor will rotate in the direction of the rotating magnetic field. Now, why does rotor rotate? Because of the relative speed. Now, what will be the rotor speed? Will it be same as Ns? Let us consider they are same. Ns equal to Nr. That means rotor is rotating in the speed of rotating magnetic field. What will happen? Then if the rotor rotates with the same speed of the rotating magnetic field, the relative speed between the rotating magnetic field and the rotor will be zero. If their relative speed becomes zero, that means rotor is rotating and the rotating magnetic field is rotating and they are having the same speed, so the magnetic field cutting will be 0 because relative speed is 0. So if there is no magnetic field cutting, there will be no induced EMF in the rotor side. If there is no induced EMF in the rotor side, there will be no rotor current in the rotor side. If there is no rotor current, so there is no reason for the rotor to rotate. So rotor will try to stop. When rotor tries to stop, what will happen? It will try to reduce the speed. Then when the rotor tries to reduce the speed, there will be a relative speed between them. That means rotor speed is lower than the rotating magnetic field speed. So there will be cutting of magnetic field, and due to cutting of magnetic field, induced EMF will be there and current will be flowing, and to oppose that current, again rotor will try to speed up. Due to frictional effect and other effects, rotor will try to catch up that speed but will never be able to catch that ns speed. So the rotor speed will be always less than ns, because if rotor speed becomes equal to ns, then there is no reason for rotor to rotate because there will be no magnetic field cutting. So rotor speed will be always less than ns. So ns is always greater than nr, or in opposite way we can say nr is less than ns. So I want all of you to keep this in your mind, that rotor speed will never be able to catch up that ns speed, that means synchronous speed. Rotor speed will be always less than ns, synchronous speed. And the difference between ns and nr with respect to ns is termed as slip. So what is slip? Slip, generally denoted by s, is equal to ns minus nr over ns. Sometimes slip is represented by percentage of slip. So percentage of slip s is equal to ns minus nr over ns into 100%. This slip value for induction motor ranges from 0 to 100%. Actually, practically it's not possible to get slip value equal to 0. It's not possible practically. Slip equal to 0 for an induction motor. However, for induction generator it's possible, but that will be described later. So the slip ranges from 0 to 100%. At stationary, at stationary, that means when the rotor is stopped, the value of nr equal to 0. That means rotor is not rotating, so the rotor speed will be 0. At that moment, the slip value will be s equal to ns minus 0 over ns equal to 1 or 100%. So at stationary, the slip value will be 1 when the motor is stopped. So whenever motor is stopped, we'll say the value of slip is 1. But when the motor is running with synchronous speed, though it is not possible practically, then slip value will be ns minus, if the rotor is rotating with the synchronous speed, so nr will be equal to ns. So we can write ns over ns equal to 0. So this is not possible practically, but if the rotor rotates with the speed of synchronous speed, then the value of slip is said to have 0. If we plot the curve for slip versus nr, suppose this is the rotor speed and this is the value of slip, this is 1, this is 0 value, this is 1 value. So when nr equal to 0, the value of slip will be 1. When nr equal to ns, the value of slip will be 0. So if we plot the curve, it will have a straight line like this, and this portion, and we have two different portions. Actually, there are three regions. This is the motor region. In this region, we have NR is less than NS. This is the region where NR is greater than NS. When the rotary speed is greater than synchronous speed, then this this portion is termed as generator region. Generator region. Actually, what's happening? We are giving more speed than the synchronous speed, so we need to give some external force to the rotor shaft so that it can move with the higher speed than the synchronous speed. Then whenever we are giving external force to this motor, and that is causing the rotor to rotate with a higher speed than the synchronous speed, then it will act as a generator. This portion will not be covered in this course, but I want all of you to know that when we have NR is greater than NS, then this will become generator, and this type of induction generator is used for wind turbine. And here we have NR negative. Negative means if we consider that this direction is the positive, that means clockwise direction, then negative will be anti-clockwise direction. So NR is rotating in the opposite direction of the rotating magnetic field. So we have NS in this direction and NR is rotating in this direction. Then for this red one, this region is called braking region. Braking region. We'll start from this braking region in the next lecture. Up to this much today. Thank you.